All right, so there's a comment in the chat about how Markov chains have been used in nuclear physics already. I am not surprised. Markov chains are a fairly powerful mechanism, and they've been used for modeling all sorts of things. So I would not be surprised that they're used in nuclear physics. They're used in economics, they're used in finance, they're used in chemistry, in applied math. So I would not be surprised that they're used to model phenomena in nuclear physics, right? So any system where you have sort of this history-free property, so where the current state of your system tells you everything you need to know about the system, so the path you took to get to the current state doesn't matter, and that alone can tell you how the system will evolve into the future, you can probably model using a Markov chain. I think Markov decision processes are maybe not as widely known. I think this is much more specific to the specific areas of optimization and reinforcement learning that study these things, right? So decision theory and maybe certain branches of economics where this kind of agent-based modeling is a standard tool of the trade. Okay, so as I said near the end of this slide, let's now consider the scenario where we don't know the dynamics of the world and we don't know the reward function, right? How are we going to learn a policy when we don't know anything about the world? And it may seem amazing that this is possible at all, but it is, and this is currently where a lot of current progress in reinforcement learning is, using algorithms like Q-learning. Now, the classic Q-learning algorithm is actually not that old. It dates back to the 80s. What is new is combining this with sort of deep learning and deep neural networks, and we will get to that in a minute. But before we get there, we need to understand how exactly Q-learning solves this online reinforcement learning problem, right? And the central sort of definition that we're going to need to work to understand the Q-learning algorithm is this notion of a state action value function, or what I'll simply call the Q function, right? So the definition is there on the slide. I won't repeat it, right? But note that it's slightly different from V star, which is what we've been looking at all this time, right? So V star says, if I start in state S and act optimally every step of the way, what is the expected sum of discounted future rewards I can get, right? That is the true value function. Q star allows you to deviate from acting optimally, potentially acting optimally on the very first step. So Q star is doing something like the following instead. So I'm in some state S. On the first step, I'm going to take action A, whether it's the optimal thing to do or not. And then thereafter, I'm going to behave optimally, right? So I'm going to take decisions according to pi star. So if I were to follow this trajectory, so take action A on the current time step and then follow the optimal policy thereafter, then what is my expected return, right? That is what Q star is capturing. And once we have that picture in mind, we can see that we can relate it back to the things we're more familiar with at this point, right? So in particular, we can relate V star to Q star, right? So if you think about it, oops, so sorry, Windows getting in the way. Let me just move that out. So Q star says, I have to take action A in this current state and then act optimally thereafter. V star says, if I'm in state S, what is the value of acting optimally every step of the way, including in the current step, right? So the only difference is what we do on this first step. So if we want to relate these two things, then to recover V star for given Q star means I should probably act optimally on this first step too, because acting optimally thereafter is already folded into this definition. So to make sure I pick the best action in the current state, well, we've seen this trick before. So we just want to say, pick the best action in the current state, right? So pick the action that maximizes this quantity on the current step, and that will give me back V star, right? And somewhat analogously, if I want to extract the optimal policy, so if I've somehow managed to already learn Q star, is there a way I can get the optimal policy out of it? Well, yes. Notice that Q star already encodes acting optimally in the future. So the only thing I need to make sure I do is on the current step that I act optimally. So I want the action that gives me the maximum Q star. So in this case, we take the argmax. Right. So if my handwriting's a little hard to read there's a nicer LaTeX version of those equations. I'm going to pause here for 30 seconds and make sure those equations make sense and see if folks have any questions. Right, so again, why are we doing this? And that's a legit question. So the full payoff is not going to be apparent here for maybe another couple minutes. But in principle, right, if we were able to successfully learn this Q function for every state action pair, then this pair of equations tells us that the Q function is all you need, right? Because if you have the Q function, you can get the value function out if that's what you want, and you can also get the optimal policy out if that's what you want. So this one can do double duty. If we're able to learn this thing well, then we are home and dry, right? So there's a question in the chat, is there a math expression for the Q function? That is exactly where we're getting. So I think what you mean is we set up this equation for the value function, right? We had this Bellman equation for the value function that related the value of one state to the values of its successors. And is there something equivalent, some recursive expression that's equivalent and does the same role for the Q function? So you kind of just predicted where I was going next. So this is exactly what we're going to do next, right? Can we relate, can we recursively express, come up with an expression for this Q star function? So yes, we can, right? So Q star, so what is the expected sum of discounted future rewards if I take this action in the current state and then behave optimally thereafter? So what is going to happen? Well, I'm going to get the immediate reward associated with this state, right? And let's maybe add an index to the state just so it makes things a little cleaner. So I will collect an immediate reward and then the usual mouthful of qualifiers, right? Discounted sum of expected future rewards. So there's my discount factor. And now we need the expectation term. So after I take action A in SI, I could find myself in a whole bunch of states SJ. So I will weight each of them by the appropriate probabilities. Notice my action A is already fixed. So that's nice, right? I don't need to take a max here or anything because the Q function is only interested in valuing this specific action in this state. So my action is fixed. And now I need to multiply this by what I can expect to receive in the future having taken this action, right? And this is where this key part of the definition helps us out. We're now going to assume that in the future, this agent is now going to act optimally. It's going to take the best possible actions moving forward, right? So if the agent does that, that is then we should take the state SJ we find ourselves in, and the value of acting optimally in the state forever into the future, well, that's precisely the definition of V star. Does that make sense? Okay, so if we have this, Well, this is not quite a recursive expression because Q star doesn't, we've written Q star in terms of V star, but hey, look, we figured out how to rewrite V star in terms of Q star. So let's just substitute that back in. So we get a nicer looking thing, which is an equation only involving Q star, right? So V star of Sj is the maximum over all the actions. The one thing we have to be careful about is there's already an A in this expression. So I want to be careful and maybe change this variable so I don't accidentally capture it. So maybe we'll call it A prime instead. Right? So here is the central equation we need for Q learning, right? So this is a form of the Bellman equation for the Q function, right? So we were able to easily express it in terms of V star, but then V star has a straightforward sort of expression in terms of Q star. So just substitute that in and you get a purely recursive equation for Q star. And much like with with value iteration, this is for MDPs. This is not a linear system again. We have this max term, which is a little annoying. So you can't solve this with just linear algebra. We're again going to have to solve this with some iterative procedure, right? So, so there is the Bellman equation. I'm not sure. Let me clear all of that, right? So this is the thing we just derived. Now, before we can run with this, we still have a problem, right? Which is this probability still crops up in this equation. And the whole conceit of Q learning is that we want to learn in a setting where we don't have access to these probabilities, right? So remember, we're now in a setting where we don't know how the world works. So we don't know what the contents of that transition matrix are, right? So how do we figure out how to make these updates, which we can do iteratively like we did for value iteration? How do we do these updates when we don't know what these probabilities are? Well, if you squint at it and look at that thing again with fresh eyes, you'll notice that what this is it's essentially an expectation calculation, right? It's probabilities multiplied by some values and summed up. So this is some kind of expected value. And a standard trick when you're trying to compute an expectation is you can always replace it with a sample mean. So I'm trying to compute the average of some quantity. Well, I don't know precisely what that is. What I can do is just draw a bunch of samples and average them together, right? So that's precisely what we're going to do. So we don't have access to these probabilities, we'll estimate them with a sample mean instead. So if we're being more careful, this is kind of what that looks like. So let's just take an example of how this might work just to see what that might look like. So I find myself in some state S. I want to evaluate Q of SA, right? And maybe there's some underlying probability that governs these transitions, but I don't know them, right? So when I'm in state S and take action A, sometimes it'll take me to state S1, other times it'll take me to state S2, but I don't know what these true probabilities are. So if I did, I can just plug them into this equation, right? If I knew what P1 and P2 are, I could plug them into this equation, but I don't. So how can I compute the value of this equation when I don't know P1 and P2? Here's what I can do. So this is what I meant about the sample mean. We simply draw episodes. So in other words, when we're in state S, we simply try action A. Right? So the agent is in the world, it simply tries action A and observes the transition that happens. So maybe this first time it observes a transition to state S1. So we will go ahead and record this quantity, right? So the sum of the reward and then gamma times the actual transition that we observed, right? And we'll do it again. And the second time I try action A in state S, the same transition happens again. And we'll do it again. And this time, the third time I tried the same action, something different happened. So it took me to state S2 instead, right? So my expression changes slightly, right? It accounts for the fact that I ended up in S2 instead. Do it a fourth time, maybe I go to S1 again, right? And we can do this many different times. So let's say we pause at this point and we decide to average those things together. Notice what's going to happen. So we'll have 4 RSs divided by 4. So that's just an RS. And then gamma factored out times 3 out of 4 times I went to S1. So that's this term. And then 1 out of 4 times I went to S2. So by looking at the empirical transitions, it turns out that I can just add the transitions, the outcomes of the transitions as I go and average them. And the law of large numbers says that in the limit, the transitions will happen in exactly the same proportion as the true probabilities dictate. So I don't actually need to try to estimate these things very carefully. I just do things in the world. I record the transitions, and then I average the returns, and things will get added up in the right proportions for me. Right? So are you probing the probability? I'm not sure. So maybe the way I've set this up right now makes it seem like we will put our system in state S and try the same action over and over, which is certainly one thing you can try to do. But in practice, in many domains, it may not be that easy to put your system in a specific state on demand, right? If you think about playing like an Atari video game, it may be hard to reach a very specific configuration of the game on demand. I may have to take a series of actions to get to a state. So, so in practice, we don't actually do what I just did. So though the intuition still carries over, right? So instead of putting our system into a specific state and trying the same action over and over and carefully evaluating this, we'll just average as we go, right? So when we're trying to compute this, we will average as we go, meaning the equation actually looks something more like that, right? So in specifically, at all times, I maintain my current estimate of QSA. So imagine a giant lookup table, which tells me for every combination of state action value pairs, state action pairs, what the value is. I maintain some running average. And every time I observe a new transition, I incorporate that into my running average, right? So that's what's going on here. So specifically, if I pick 1 over n plus 1 for alpha, right? You can expand this out, and you'll see that basically what this computation does is take my current average for Q, take the new sample into account, and then recompute this average, right? So it's just a running average. So doing it this way means I don't have to go through my states in a specific order and do them one at a time. Instead, I will just go into my environment and act as appropriate, and I will just update the SA entries for the actual state action pairs I encounter along my trajectory, right? So I'm not forced to do things in a specific order. I'll just update the portions of my table that I actually encountered as I went through and acted in this world. How do we get alpha here? So 1 over n plus 1 is certainly one choice, right? But in more generally, alpha behaves like a learning rate parameter. So in practice, people just set this the same way you would set a learning rate. So the idea being that if I set this to a large number, then I learn quickly, which in this context means older samples quickly get overtaken by new samples. And if I set this to be really small, then my samples get sticky, right? So old things continue to influence my running average well into the future. So this is essentially a learning rate parameter. And you find the best way to set this by trial and error, right? So experimentally, you would set it like you would set any learning rate, right? This equation essentially in a nutshell encapsulates all of the Q-learning algorithm, right? So initialize your table randomly, then send your agent out into the environment and let it act according to its current policy. Observe all the transitions you see, right? So each state, action, state, action, state, action sequence. And when your episode ends, so for example, if you're playing a video game, at some point you're going to win or lose. So that's the end of an episode. Then you take every state action transition you saw and you update the running averages for all of them using this equation. And then you would start a new episode, and you start a new episode, and you start a new episode, right? Let's address the elephant in the room. I alluded to this maybe during the break. What if my state space is large, right? So I said, well, just maintain a lookup table, right? But if my state space is exponentially large, then you cannot store this queue function in a lookup table, right? You cannot have a giant table that gives you what the value is for every state action pair, right? If you're talking about games, combinatorial games like Go or chess, the number of chess positions is more than the number of particles in the observable universe, right? So you are not going to be able to build that table in our current universe. So clearly this is a non-starter. And even for sort of more modest domains, you're not going to be able to explicitly represent this queue table. So this is where the idea of function approximation comes in. So meaning we can't store the lookup table, but we'll approximate the lookup table using some sort of supervised learning model. So you can use, so remember the thing we're trying to predict, this Q star is a real number. So we have a regression problem, right? So I can't explicitly store the value of this function at every point I care about. Instead, I will store some smoothed representation of that table using a linear regressor or a support vector regressor or a decision tree or a neural network, right? Anything that's capable of doing regression, right? So we'll still do Q-learning, but we'll also fold in some supervised learning. And essentially that's going to involve taking this Q update equation and treating this new sample estimate of the Q value as though it were our target, as though it were the target for our supervised learner, right? So for example, if you had a neural network as your function approximator, so this neural network would take your state and actions as inputs. Some neural network magic will happen in here, and it's going to spit out a Q star, right? So you can use this network to guide your agent's behavior. When the episode ends, you would be able to collect this information and use these as your target values to do your backpropagation step and update all these network parameters. Right? So instead of updating a lookup table, you would update the network parameters in a manner that the Q function moves closer to these targets. So you turn it into a regression problem, this problem of maintaining this Q value table. Does that make sense? Okay. So, whoops. In the specific case where we use a deep neural network to perform the role of this function approximator, you recover the now famous DQN algorithm. So this was DeepMind's paper from 2014, where a system started from a randomly initialized policy, and then through a process of trial and error, learned to play 49 different Atari games to various levels of performance, right? And it's basically a combination of all of these ideas so far. So you start with, so you use the classic Q-learning algorithm, but you combine it with a deep convolutional neural network for representing your Q function approximator. So the convolutional neural network takes the raw pixel inputs from the game as its inputs, right? So this neural net, this CNN that we have, takes pixels that have been appropriately pre-processed, and then what it spits out is for each action your agent can perform, right? So if you think of your Atari controller, you have a joystick with a bunch of buttons. So for each button that you could press, it outputs a Q value. Right? So in one forward pass, you get the Q star value for every action you could have done. And amazingly enough, with even just raw pixel inputs, this system was able to learn to play a wide variety of games that have very different dynamics, very different reward structures, very different sort of gameplay dynamics, right? So a couple of things that really made this work, especially when you're combining Q-learning with deep neural networks. One big problem is, notice how we train this neural network, right? So our agent goes through and plays out one episode of a game. That means you start at some initial state and you perform an action. And then you go to another state, you perform an action. You go to another state, you perform an action. And this goes on. And then your episode ends at some point, right? So notice what I said. What we would do at the end of the episode is take each of these state action pairs, attach to them a target value, which is given by that equation for the Q function, and then update your network parameters using that as your training set. The problem is this sequence tends to be heavily correlated, right? The state action pairs all come from a very narrow area of your training space, and the Q values are also all going to be very close to each other. So when you train a neural network on highly correlated data like this, your parameters can move in very dramatic directions, right? Because you're essentially oversampling from a narrow part of your state space. So one way to break this correlation in your training set is to use a technique known as experience replay, which was something that was folded in to the DQN paper. Again, this is an idea that dates back to the 90s, but basically what that means is when you collect experience from a current episode, you don't use just this to train your network. Instead, you also keep a replay buffer, which is a record of past episodes that your network played as well. So if you think about your network playing many, many hundreds of thousands, millions of games of, say, Breakout, you would keep the traces from many of them into the past. So when it's time to do a batch update to your neural network, you don't just use this most current episode as your training data, but you mix and match. You may draw a few examples from here, but you would also draw a few examples from the past. So by drawing training examples from across different episodes, you are breaking correlations. So your training set becomes a little less correlated and it stabilizes the learning. So this was an important trick to make sure that your neural network did not, that it was stable and it wasn't fluctuating wildly. The other important trick was the use of a target network. So the idea here is you don't maintain one neural net, but actually you maintain two, right? And we'll call this one theta and this one theta prime. So we have two neural networks, right? So the idea being that we will collect experience using this neural network, right? So when we play out the game, this neural network will guide my policy and my agent will act according to what this neural network tells me. And when it's time to update the parameters, I will actually update this neural network instead, right? So, and then periodically, I will clone the weights from this network into the other one, right? And the reason we want to do this again is essentially for learning stability reasons, because if we don't have these two separate neural networks, then essentially your policy is guiding you in what to do, and then you instantly use that feedback to update the current network, which will shift your policy in unexpected ways. So you create this complicated feedback loop, which again destabilizes the learning. Excuse me. So to stabilize things a little bit, you use a target network, which will produce slightly more stable targets that your other network can aim for. And then periodically you clone the network so that you keep this one roughly in sync with the current policy of your neural net, right? And then there's a bunch of other tricks that we use that have to do with how you specifically pre-process some of this pixel input, but those were maybe more domain-specific tricks, right? Specific to how Atari games work and how you want to feed that input. But this is essentially the DQN algorithm. So bringing together several different tricks, right? So several different ideas, none of which were particularly earth-shattering in and of themselves, right? We had made independent progress in each of these problems, admittedly across different decades in AI history, right? So Q-learning, the idea is from the 80s, so we still use that classic algorithm. Deep CNNs, well, those only really started gaining currency in around the 2010s. And then experience replay was again an idea from the 90s. And I believe the target network was something new introduced by the DeepMind people. But one of the main contributions was bringing sort of all of this together in one paper and really bringing it together in one impressive demo of what you can do, right? And like I said, what ended up being a $500 million demo, if you will, right? Because shortly after DeepMind released a preprint of this paper, they were acquired by Google for something like $600 million. So, so maybe the most profitable paper, arguably, in the history of science. So that is the deep Q network algorithm. In the remainder of our time together, I would like to briefly talk about an alternative way to do reinforcement learning. So in some sense, you can think of Q-learning as the value iteration analog of reinforcement in reinforcement learning. So we learn a value function, so this Q function, and then use that to figure out a policy, right? So much like with MDPs, we can ask the question, well, if a policy is ultimately what we're interested in learning, then why go through and do this circuitous thing where you learn a value function first and then you extract a policy from it? Could we just directly extract a policy instead? And the answer is yes. And this insight leads to this family of policy gradient methods, which is maybe the second big family of reinforcement learning algorithms you should be familiar with. And the intuition is exactly what I just described, right? So if the policy is ultimately we care about, then why don't we just try to learn it directly? So let's not take this detour to learn Q star and then use that to find the policy. Let's just learn the policy directly. So how are we going to do that? So why might this be a good idea? Let's start there. So, well, it's always a good idea to be optimizing the thing you care about directly when you can. But the other sort of subtle thing about these policy gradient methods is that they also enable us to learn in settings where your actions may be continuous in nature, right? So remember in Q-learning, we have this max term over, right? So there's a bunch of other math around here, but this max term appears in our Q function update equation. And well, if my action space is continuous, how am I supposed to take this max? So you end up with, well, you can't iterate over the actions because this is a continuous action space. I guess you could do an inner optimization loop that tries to find the best action in some sort of gradient ascent kind of way. But of course, that's adding a whole lot of other complexity. So policy gradient methods sidestep this issue neatly because we'll see that this tricky problem goes away. The downside is a little more subtle, and it happens to come from the fact that learning a policy directly in general leads you to creating what are known as on-policy learning algorithms. And what that word means is basically that the way I improve my policy is by using experience collected using that policy, right? So when we talked about Q-learning just a second ago, we didn't have that restriction, right? Because the Q function doesn't really depend on the policy my agent is following at any given time. Because the Q function is mainly concerned with figuring out what value to attach to the state action pair, right? It's independent of my agent's overall policy, right? My policy can do whatever it wants. That has no bearing on how to value an action in a given state. So in some sense, what this means is we can do things like use experience replay in Q-learning, because even if I collected my experiences in the past using a different policy, they are still useful in figuring out how to value actions and states, right? In contrast, if we're doing policy gradient-based learning, then I'm trying to update the policy directly, which means I need to know how the current policy is doing, and I can only use traces drawn from the current policy to update this policy. If I go back in time and pick old training episodes and try to use that to update my new policy, I'm going to be using stale data, because that data bears no resemblance to how my policy is acting right now. So that's what I mean by less sample efficient, right? You're going to have to collect way more data to make your policy updates, because I don't get to reuse data from the past, which I can do in off policy methods like Q-learning, right? So the general idea for how we implement a policy gradient approach. So the first change in perspective is we'll move away from deterministic policies to what are called stochastic policies. So recall, till now, we've been dealing with deterministic policies when talking about Q-learning, where for every state, my policy simply told me, here's what you do. Instead of this, we will now represent our policies as stochastic policies. And what that means is, if I'm in a given state, my policy will give me a distribution over the possible actions. So for example, it may induce a distribution like this. So what it says is, if you're in state as perform action A1 with probability 0.6, perform action A2 with probability 0.3, A3 with probability 0.1. And the way my agent acts is by taking this policy and flipping a coin, so by sampling from this distribution. Right? So my actions will be stochastic. Going to pause here for a minute and see if folks have any questions. It's also been a little quiet on the chat, so I just want to make sure that I'm still connected. Folks still with me? Everything good? Excellent. Yeah, it's always a little off-putting because I can't see any faces, so there's no feedback whatsoever. So if there's nothing in the chat, then I don't know if I'm just talking to a camera by myself. All right, glad to hear everyone's still here. So this is a stochastic policy, right? So instead of telling me exactly what to do in a state, it gives me a distribution, and I would sample from this distribution. So flip a coin, and that tells me what to do. This stochastic policy will be parametrized, and we can use, say, a neural network to represent the policy, right? So what that means is I'll have some sort of neural net, right? Inputs go in, so my state goes in, and the output of my network will be a probability distribution, right? So this is how I will represent my policies, right? So for a given state description goes in, neural net does its thing, and out comes some probability distribution. So it's almost, you can think of this as a multi-way classification problem, right? So you output a distribution over the actions, and you can sample from that, and the agent can take whatever action was picked. And once we have that all set up, we're good to go, right? So if my policy can be directly represented by a neural network this way, then great. We know how to optimize neural nets, so let's just do that directly. So we'll just use some sort of gradient-based optimization. And the general intuition is going to be to collect some episodes of training data, and then based on that training data, adjust the probability distribution so that you encourage good actions and discourage bad ones. So general roadmap makes sense. So essentially, it's again just this trial and error idea. For a state, initially, I may start off with a completely, purely, uniformly random policy. But as I collect experience, these probability distributions will drift away from the uniform distribution to other more sensible distributions. And the way we would do that is by precisely reinforcing good behavior and discouraging bad actions. Right. So how we make all of this work is going to occupy the rest of our time. So how exactly do we update the network parameters? So how do we do those gradient updates? So the first thing we're going to do is give this expression, which has that which is a mouthful, right? So this is my discounted sum of future rewards. And I'm going to give it a more convenient name. We'll call it the return. We'll write it with that notation, just so we don't have to say this out every time. And if we assume this parameterized stochastic policy, so a neural network representing my stochastic policy, then it's clear what we want to do, right? The goal of our algorithm, this policy gradient algorithm, is to find my neural net parameters that maximize this thing, right? So that's what we want to do. So, or written out in math, this is the optimization problem we want to solve. Right. So what is tau? I'm using tau to represent my trajectory, right? So tau is simply a sequence of states. So S0, S1, S2, so on, right? So this is simply the states I encountered during an episode. So it's one trajectory. Right? So the thing we want to maximize is the expected return over all the possible trajectories that I could encounter, right? So if I decide to follow this policy induced by my current neural net, so following that policy can lead to a variety of trajectories, because remember, my environment is stochastic. So even if I take the same actions over and over, the non-determinism in my environment may produce different trajectories. So we will average essentially over all those trajectories. So that's what this expectation is saying, average over all the trajectories. And what we're interested in is the return of each of those trajectories, right? So what we want to do is maximize this whole thing, right? So I want a policy which ensures that on average, my returns are as high as they possibly can be. So if we call this expectation J, then this is the optimization problem. Find the network parameters that make this thing as big as possible, right? And how do we do that? Well, standard optimization, except you'll notice from the sign here, we are going to do gradient ascent, not gradient descent, because this is not a loss function, but this is my expected returns, right? So this is my reward instead. And I want my rewards to be as high as possible. So instead of going in the negative direction to the gradient, I want to climb, I want to do hill climbing. So we'll instead move the parameters in the direction that increases J, right? So move it uphill instead of moving it downhill. Right? So standard gradient descent says, well, just take your parameters and update them in the direction of the positive gradient of this thing, right? And alpha here is my learning rate, right? So standard tricks so far. So I see I have 1 more minute. So what I was going to do next was essentially derive what we do about this gradient, right? So this gradient, how do I find an analytical form for this gradient given this definition? Question in the chat. So why standard gradient descent? What if it's a local maximum? So gradient ascent, I guess, because, well, local maxima is just a fact of life, right? So when you're doing optimization of these functions that can be highly non-convex, local maxima are always a problem, but it is what it is. If we are trying to strike a balance between solving for a good set of parameters, but also doing it in a computationally tractable way. And yes, you're right. There may be local maxima, Oh, yes. This would be stochastic gradient ascent. I understand the question. Yes. So we would, so maybe a little loose with my words there. Yes, we would be doing stochastic gradient ascent. And in a sense, we don't really have any other choice because it's not like we can, stochastic gradient ascent becomes even more of a necessity here because remember, we are going to draw trajectories in the environment. And when an episode ends, that's when we will treat that sequence of events as one mini batch and do gradient ascent. So it has to be stochastic gradient ascent. It cannot be the batch form anyway. Right. So the question is, how do we derive this gradient? And I was going to do this explicitly. So, but in the interest of time, I'm just going to say, well, there's some math that goes in here, right? So most of it's fairly straightforward. And it's just playing around with the gradient and performing a few algebra tricks to get to a final expression. So I'm going to skip the derivation, but it will be a part of these nice video lectures that Morten promised you all earlier yesterday, I believe. So if you are curious about the derivation, the final sort of the Hollywood version of this video will contain the full derivation. So in the interest of time, just take my word for it today. I guess we can do some math here. And if you do the math right, we will get to this place. So we will derive an estimate of the gradient, which looks something like this, right? Where will these extra videos be? So we will link to them from the GitHub page, right? So they will be linked to from there. So again, we want to perform gradient ascent. We don't know what this gradient is, but we can estimate it using this expression whose derivation I skipped. Right. So, but the thing about this expression, even though it's a little mysterious, is the important thing to take away is this is all something, the only things in here are things we can compute, right? This R of t is simply the reward, the return, right? So it's the sum of discounted rewards from my episode. So we know how to do that, right? Because my agent simply takes actions and I can observe the rewards I collect along the way. And once I've collected them all, I can sum it up and discount them to compute the return. This gradient of the log of my policy, well, pi of theta, remember, is my parameterized stochastic policy. This is simply my neural network's output. So this is the output of my network. Taking the log of that output is also straightforward, and computing the gradient of the log, well, that's what we have our automatic differentiation packages for. So TensorFlow or PyTorch to the rescue, right? So all of these things are things we can compute. Summations, computers can do that. And this outer summation is essentially saying, so what are the two summations for? So this is summing over, so we would go out and collect a set of trajectories. So let's say n trajectories. So that's what the n is. And then this summation is over the length of each of these trajectories tau. So if each trajectory lasts some finite number of steps, then we are summing over the length of each trajectory. So, and this expression is claiming that this is a decent estimate of this gradient. And if we have that, we are golden because we can just plug this into this expression and we can update our network parameters and start doing gradient ascent. And we would directly be updating our policies in the direction that improves them. So instead of performing this update, we will perform this update, right? So, and a couple of tricks that enable us to do this well and stabilize the learning. Again, one thing about this gradient estimator is that it can be fairly noisy. So there are various tricks that are used to make this a low variance estimator so that these gradient ascent steps are a little more smooth instead of having a lot of jitter in them. And usually lowering this variance involves replacing this return term with other expressions in its place using so-called advantage estimators. And there are a variety of things you could plug in here, and those will help smooth the learning, right? So that is one improvement we can do. The other key innovation in maybe the last 2 or 3 years has been the use of these so-called trust region updates, which comes from the insight that, okay, so my neural network is representing the policy, but we know this about neural networks: they're highly nonlinear systems, which means when I make this gradient ascent step, even if the change to my parameters is fairly small, a small change in my parameters can still produce a very dramatically different policy, right? So we want to avoid that, because if you have wild swings in your policy, then the learning gets very unstable and you can have a hard time converging to something good. So the trust region idea says, when you do these gradient updates, we'll add some mathematical machinery in here to ensure that after you've done the parameter updates, that the new policy stays roughly close to the old policy, right? And remember, the policies are just probability distributions. So there is a way to express that compactly using measures like the KL divergence, right, of two distributions, if you know what that is, right? But basically, you can come up with measures of telling whether two probability distributions are close to each other or not, and we just incorporate some terms like that in our gradient estimator to ensure that your updates are not too crazy, right? So we will end here, and let me briefly summarize what we've just talked about today. And basically, your takeaway message is, if you have a sequential decision or a control problem, then reinforcement learning may be the solution, right? So this may be a way out. So a good place to start is to think about your problem and see if you can model it as a Markov decision process. And if so, then RL might be able to help you out, right? And in particular, deep RL is kind of the hot thing right now, which essentially involves combining classic reinforcement learning algorithms with these deep neural networks. They can be somewhat challenging to use and tune. They have a lot of hyperparameters, and the learning can be somewhat brittle. And what that means is that sometimes this can be sort of an exercise in frustration, finding just the right hyperparameters to make things work. And this is actually an active area of research in deep RL right now, figuring out how to make these RL algorithms more robust and make them better behaved. But if you are just exploring some problem you have, then the PPO algorithm, which stands for proximal policy optimization, is a good default algorithm to start with. Right, so if you have an RL problem, you think you can formulate it as an MDP, then PPO, which is a policy gradient algorithm, which incorporates some of these tricks. So incorporates variance, reducing advantage estimators, incorporates trust region updates, is a good default algorithm to try first. And importantly, you don't want to be a hero. So don't try to re-implement these algorithms from scratch. There's a lot of hairy math in there. And it's easy to have subtle bugs in your code, which your algorithm may still learn something, but it may still not be correct. So RL algorithms are notoriously difficult to debug. So there are high quality implementations available. So for example, there is the stable baselines repo, which you can find on GitHub if you Google for it. So this is a project that builds on an original project that was first started by OpenAI, and it has since been adopted and made better by other researchers. And this is the place I would start if this is something you're interested in exploring, right? The stable baselines project which has implementations of many of the common reinforcement learning algorithms, including DQN and PPO, which we just mentioned briefly. So we will stop here. I guess this is the conclusion of sort of the standard material in our workshop for this year. I believe the director of ECT STAR, Professor Wambach, is also on this call and is briefly going to address you all before we wind up and return for the Q&A session. So let me go ahead and stop the recording.